We are going to cover topics that include endothermic, exothermic, specific heat, catalysts, and reaction rates. Some things to keep in mind is that in order for a reaction to occur, molecules must collide. Remember, 3 things must happen in order for a reaction to occur. The first is a collision. The reactants must collide and hit each other. The second is orientation. The reactants must align properly in order to break and form bonds. If they are not hitting each other at the right angle or the right spot, they will not break and form new bonds and not form a new reaction. The third is energy. The collision must provide the energy of activation. Let's think of this as the energy required to climb a hill. You must have enough energy to get that reaction started. Now we're going to talk about endothermic and exothermic reactions. In an exothermic reaction, heat is released. Exo means out, so when you exit or exo the building, you are going out of the building. The energy of the products is less than that of the reactants. So here we can see the energy of the products in the graph, and it is much less than that of the reactants. Also on the graph, we do see the activation energy. This activation energy is the amount of energy it needs to overcome and for a reaction to occur. Additionally, in an exothermic reactant, heat is a product. So you will see the heat on the right-hand side or the product side of an equation. Another type of reaction is an endothermic reaction where heat is absorbed. Endo means within. Endothermic reactions typically also feel cold to touch. What helps me to remember this is endo has a D and the word cold also has a D. In an endothermic reaction, the energy of the products is going to be greater than that of the reactants. Here we can see the energy of the products. It is much higher than that of the reactants. We can also see that the energy is on the reactant side, and there is way more activation energy that must be overcome in order for the reaction to occur. Take a few minutes, pause the video, and try to identify these as either exothermic or an endothermic reaction. Let's check your answers. Did you get these right? The first is exothermic because heat is on the product side. The second is endothermic because heat is on the reactant side. And then the last one, heat is on the product side. So again, it's exothermic. Now, what is another way to determine if it's exothermic or endothermic and it's not written in the equation? We can do some math. We can figure out how much heat is gained or lost by solving for Q. The equation we would use is Q equals MC change of T. Q would be the amount of heat gained or lost. M is the mass in grams. C is the specific heat, which is a quantity of energy in joules needed to change the temperature of 1 gram of substance by 1 degree Celsius. And change of T is the temperature in Celsius. So C will change for each element or each compound. If you look at the back of your textbook, there is actually a reference table that will say the specific heat for each element or various compounds. When you solve this equation, you will either get a positive Q or a negative Q. If your Q is positive, you know that it is an endothermic reaction. If Q is negative, you know it is loss and it is an exothermic reaction. Go ahead, gather your materials, and let's try some practicing problems together. You're going to need a periodic table, something to write with, and a calculator. All right, so we're going to do a couple practice problems, and we're going to solve for Q, so make sure you have a calculator, something to write with. So we're going to calculate the specific heat capacity of a new alloy if 15.4 grams sample absorbs 393 joules when it is heated from 0 degrees Celsius to 37.6. So just a reminder, our formula is Q equals MC change of T. So in this equation, we're solving for specific heat capacity. So our Q is 393 joules. Our M is 15.4 grams. Our C is our X. And our change of T is the final minus initial. So 37.6 minus 0 is 37.6. And then we can solve for C. So we know 393 will equal 15.4 times 37.6. This is 579.04 x, and we're going to divide each side by 579.04. So then our X will equal 0.68, okay? And if you wanted to figure out what substance this specifically is, you could check the whole roster, okay? So let's do one more problem together. And then it does ask, is this equation gaining or losing heat? We know that this Q is positive here, so we know it is gaining heat and it is endothermic. All right, let's do one more. It says calculate the heat change associated with cooling a 350 gram aluminum bar from 70 degrees Celsius to 25 degrees Celsius. Specific heat is 0.9. Is the change endo or exo and why? So we know the equation is Q equals MC change of T. We're solving for our Q. Our M is 350. Our C is 0.9. And our change of T is final minus initial. So 25 minus 70 is negative 45. So then we can multiply and we get Q equals negative 14,175. And that'll be in joules. And since Q is negative, we do know it's exothermic. So make sure you do a few more practice problems and ask your teacher if you need help. Next up, we're going to talk about catalysts and reaction rates and how they can influence the different types of equations with endothermic and exothermic reactions. You can use a catalyst, okay? A catalyst is going to increase that rate of reaction. It will lower that activation energy, and it's not used up during the reaction. So if we look at the graph here, it increases the rate of reaction because the activation energy goes from the initial one down here to the smaller purple one down here. So it is a much smaller activation energy that it needs to overcome. But the important thing to remember, it is never used up during a reaction. So how do you figure out the reaction rate? The reaction rate is the speed at which the reactant is used and the speed at which the product forms. So can you change the reaction? Yep. Can you lower the activation energy? Absolutely. We just talked about it. If you make more collisions and you have more reactants, this can all help influence the reaction rate. Let's take a look at this. If we want to increase the reaction rate, we can increase the concentration. The more reactants you have, the more collisions will occur. You can also increase the temperature. The more higher the temperature, the faster those particles are moved, and they're going to hit each other more. And finally, like we already said, you can add a catalyst because that lowers the activation energy as well. Let's do a quick study check. There's 5 examples here. I want you to pause the video and tell me if each of these is going to increase, decrease, or have no effect on the rate of reaction. Let's check our answers. A increases, B decreases, C increases, D decreases, and E has no effect.